NASA is gearing up to send a spacecraft to Mars, but the sheer physical distance between Earth and the red planet presents a massive logistical hurdle. Even with our best engineering, crossing millions of miles of empty space using the engines we have today takes an incredibly long time. Shaving months off that transit time won't happen by just building a larger version of a traditional ship. It requires changing the entire mechanical process of how we generate thrust. Right now, we move spacecraft by burning chemical fuel and oxygen, then shooting the resulting hot gas out the back of the engine. The problem is that every drop of that fuel and oxygen has to be carried from Earth, and those liquids are incredibly heavy. To go faster, you must add more fuel, but more fuel makes the ship heavier, requiring even more fuel just to push that extra weight. This endless loop creates a strict speed limit, where fuel weight cancels out the speed it provides. Because of this mass penalty, chemical rockets simply carry too much dead weight to drastically cut down the travel time to Mars. Engineers have tested a lighter alternative, engines that shoot out electrically charged gas instead of relying on heavy chemical combustion. These thrusters solve the weight problem, but they require immense amounts of electricity, which spacecraft currently harvest using large solar panels. This chart tracks solar energy relative to position. As a ship travels further from the sun, panels catch fewer photons and efficiency drops significantly. Right when a Mars-bound ship navigates the darkest stretch of its journey, it experiences a severe power deficit. Solar power physically cannot sustain the required thrust across deep space. The ship needs an internal power source. NASA's solution is to place a nuclear fission reactor directly inside the spacecraft. This is the exact same process of splitting atoms that we use to generate energy in commercial power plants right here on Earth. Fission bypasses the mass penalty entirely. Because splitting a single atom releases millions of times more energy than breaking a chemical bond, the reactor doesn't require massive tanks of liquid fuel to generate heat. This chart compares the energy potential of different systems. It shows that a fission reactor generates 10 to 100 times more power than solar arrays, and it operates at full capacity regardless of how far the ship is from the sun. By eliminating the dead weight of chemical propellants and the unreliability of solar panels, fission turns the spacecraft into an independent, high-output power station. All of this massive power output directly solves the primary goal of the mission: getting to Mars faster. With the immense, sustained energy from a nuclear reactor, a spacecraft can continuously accelerate for much longer periods than a chemical rocket, which has to coast after its initial burn. Shaving months off the transit time means astronauts spend less time exposed to deep space radiation, and the mission requires far fewer food and water supplies. NASA is currently planning to test this exact nuclear engine architecture on an upcoming mission to Mars. Mastering atomic fission in a vacuum untethers us from the sun's reach, providing the raw, continuous speed required to make Mars a truly accessible destination.